A typical volume of revolution problem will give you some sort of curves, and you then have to take the area that is bounded by those curves and revolve it around a given axis, whether it's the X or Y axis or whether it's some line. So the best way of doing these problems, hands down, is just to draw it, try to picture it in your mind, and remember what we're doing. We're adding up basically volumes of very thin washers or discs. So here we have a typical problem. We're going to first start out by drawing the region. Y equals 1 over, let's see, 1, 2, 3, 4, sure. Y equals 1 over X, it looks like this, right? Oops, like that. And Y equals 0, of course, is the X-axis. The X-axis, okay, and then X equals 1 and X equals 4. So first let's figure out the region. So this is the region that we're looking for. What we're going to do is we're going to revolve this region. We're going to revolve it about the X-axis. So I'm going to put the axis in red, and I'm revolving it this way. So now the more difficult thing maybe is to draw this in a reasonable way and to be able to picture it in your mind in a reasonable way, but this is going to look something like this. And when it's revolved, it's going to be basically kind of like this. So almost like an Erlenmeyer flask, but not quite. So you got to get that picture in your mind of what the solid's going to look like when we've taken this yellow region and revolved it around the axis. And then we're going to draw the disk. So the disk in this case, it is going to be a disk because I don't have a hole. It's going to be here. Now, the radius of the disk is right there. You can see that the radius of the disk is just the y-axis. I'm not sorry, the y-axis, the y, what's the word I'm coordinate, the y coordinate of the curve. And the curve was y equals 1 over x. Okay. Now, if I look at this disk, I can see the small infinitesimal thickness is in the direction dx. It's in the direction that we're revolving around. Like so, we can see that we're supposed to then integrate. Remember what we're doing is we're integrating these disks. So pi r squared, and then it's really, it has a thickness, and the thickness is going to be dx. So this problem is not too bad because we started out with the 1 and the 4. They gave that to us. It's here, right? So x equals 1, x equals 4 was given those bounds. We don't have to look for them. We know that we're going from 1 to 4 in x. And the radius of the disk is just y, and y you have is 1 over x. So I can just put in 1 to 4, 1 over x squared dy. Okay. So I have this. But really, you want to think about looking at the picture. I'm going to make it a little bit bigger so we can see that this is the radius of the disk, which in this case is simply the y coordinate. And then once we have the integral, that's the easy part, right? This is easy enough to integrate. This is minus 1 over x squared, only for 1 to 4. Don't do what I just did and randomly drop your pi. You're gonna need that pi. So we have oh, I knew I had it wrong. I knew it was supposed to be this. Yeah. So when I integrate, remember this is x to the minus 2, and we are doing minus x to the minus 1. So I Don't not a two there. That was not right. This is what I want. And that is the answer. So that will be the area, I'm sorry, the volume of this whole thing.